In this video, we're going to continue to talk about light. In particular, we're going to talk about refraction, which is the bending of light, and we're going to talk about how mathematically you can calculate how much bending takes place. Now, if you remember, what causes light to bend is the fact that the speed of light changes when the light enters a new material. So to be able to measure how much light bends, the key is in determining the amount of bending, is to know how much the speed is changed. Now, we have an actual measurement of how much the speed is changed in all different materials by using something called the index of refraction. The index of refraction is represented with a lowercase n, and here's the definition right here. The index of refraction is the ratio between the speed of light in a vacuum and the speed of light in a given material. So n, which is the index of refraction, is equal to the speed of light in a vacuum divided by the speed of light in a given material. So n is the index of refraction. C is the speed of light in a vacuum. Now this is such an important constant that it's literally represented with a C for constant. So the speed of light in a vacuum is 3.0 times 10 to the 8th meters per second. The speed of light is 3 times 10 to the 8th meters per second. That's 186,000 miles per second. So the speed of light's pretty fast. Now, in any other material, the speed of light is something less than the speed of light in a vacuum, so n is a number that is greater than 1. Now, on your reference tables are a whole series of materials, and the index of refraction is listed for each material. So our fundamental formula, once again, is n equals c over v. And remember that the speed of light is 3 times 10 to the 8th meters per second. So a very typical Regents question is one where they might ask for the speed of light, say, in flint glass. So let's do that question. What is the speed of light in flint glass? So the first thing I'm going to do is check out my handy reference tables, and I can see that n equals c over v is what I want, where n is the index of refraction, c is the speed of light in a vacuum, and v is the speed of light in flint glass that I want. So I am going to write my formula down. So I want n equals c over v. Now I need to look up what n is for flint glass. So I have my table for flint glass, and I look it up right here, and I can see it's 1.66. I'm going to write that down. So 1.66 is equal to speed of light in a vacuum, 3.0 times 10 to the 8th meters per second, divided by v, which is the speed of light in flint glass. And I want to solve for v, but v is in the denominator. So I'm going to have to multiply both sides of the equation times v, and then divide both sides by 1.66. So I'm going to end up with v equals 3 times 10 to the 8th meters per second divided by 1.66. So v is going to equal 3.0 times 10 to the 8th meters per second divided by 1.66 So V is going to equal 1.8 times 10 to the 8th meters per second. And that's the speed of light in Flint glass. Now that I've learned about the index of refraction, telling me about how light slows down as it goes into a new material, I am now ready to be able to calculate the actual amount of bending as a wave passes at an angle from one medium to another. And the name of that relationship that lets me calculate that is Snell's law. And Snell's law says if I have two materials, and labeled N1 and N2, there's the index of refraction of those materials. If I have two materials, 1 and 2, and light is entering from one material and going into another, then the index of refraction of material 1 times the sine of the angle the light makes in material 1, in other words, the angle it's coming in at, is equal to N2, index of refraction of the material the light's going into, times the sine of theta 2, which is the angle the light makes in the new material. So the four things involved are the index of refraction of the material light's coming from, the angle that light makes when it's coming from that material, index of refraction of the material light's going into, and the angle that the light makes in the new material. Now, I had also learned before that when light slows down, when it goes from fast to slow, it bends towards the normal, and Snell's law actually tells me why. And Snell's law says that when N2 is bigger than N1, then theta 2 is going to be smaller than theta 1. So as the light comes in at a big angle and it slows down, it bends towards the normal. Likewise, if N1 is slow and N2 is fast, so if N2 is less than N1, then if that number is small, that number has to be big. So then the light, when it hits the material, bends away from the normal because this angle is bigger than this angle. So let's see where we are now on our reference tables. So we're going to go to the wave section of the reference tables, and we see some familiar formulas. We see speed is frequency times wavelength that we learn from basic waves. Period is 1 over the frequency. Learn that from basic waves. Angle of incidence equals angle reflection is called the law of reflection. We saw that happen in the ripple tank, and we also saw the laser beam did that with the mirrors. So we know light does that too. We've just learned that the index of refraction is the ratio of the speed of light in a vacuum to the speed of light in any material. And finally, we've just learned Snell's law. And Snell's law says when light goes from material 1 to material 2, the index of refraction of material 1 times the sine of the angle in material 1 is equal to the index of refraction in material 2 times the sine of the angle in material 2. Let's try a problem using Snell's law. The problem says calculate the angle of refraction when light travels from air into crown glass at an angle of 45 degrees. So the first thing that I want to do is write down Snell's law. Snell's law is N1 sine theta 1 equals N2 sine theta 2. Now N1 is the index of refraction of the material that the light's coming from. In this case it says from air. So everything out around here is air. And this is actually a block of crown glass. So everything in here is crown glass. Everything outside of here is air. So N1 would be the index of refraction of air, which I would look up on my reference tables. And N2 is the index of refraction of crown glass, which I would also look up on my reference tables. Now let's talk about what theta 1 and theta 2 mean. Theta 1 and theta 2 refer to the angles out here in the air as theta 1, and in the crown glass is theta 2. And actually theta 2 is what they're asking me for. That's the angle of refraction. So to define theta 1, the first thing you'll notice is we've put a normal, or perpendicular, to the boundary between the air and the crown glass. So light is going to come from the air and it's going to go into the crown glass. And this normal is what we'll use to measure the angles. So you can see now we've drawn a ray that represents the direction that the light is coming in and hitting the crown glass with. And that's going to be theta 1. So the angle between this light ray and the normal, that's theta 1. Now we've added the light ray that represents the path the light has taken inside the crown glass. So the light in the air goes like this, and then it gets to the crown glass and it bends into the crown glass. And that forms this angle right here, and that angle is theta 2. So the angle that is made in here, theta 2, and that's actually the unknown. That's what we want to figure out. Now, to be able to use Snell's law, I am going to need N1, index of refraction in air, and I'm going to need N2, index of refraction in crown glass. So I use my reference tables and I see index refraction of air is 1.0, index refraction of crown glass is 1.52. So let's put the numbers in. So 1's our air, so the index refraction in air is 1.00 times the sine of 45 degrees, and that equals the index of refraction in crown glass, which is 1.52, times the sine of the angle in the crown glass, and that is my unknown. So I calculate the sine of 45 degrees and multiply it by 1, and I get 0.707, and that equals 1.52 times the sine of theta 2. Now to solve for sine of theta 2, I need to divide both sides by 1.52, which will make those cancel. And I get divide this by 1.52, and I get 0.465 equals sine theta 2. Now 0.465 is not my answer, it's actually the sine of my answer. So I have to find out from my calculator what angle, if I took the sine of it, would give me 0.465. So in my calculator, it looks like the button is sine minus 1. So what I want to do is type in 0.465 and hit sine minus 1, and that'll give me the angle. And when I do that, inverse sine of 0.465 rounded off to the nearest degree is 28 degrees. So I had to calculate the angle of refraction when light traveled from air, which is out here all the way here, into crown glass, this is the crown glass, at an angle of 45 degrees. So the question was asking me, what would this angle be? And my answer was 28 degrees. So you can see that this angle is smaller than that angle because the light bent towards the normal, and that's because light travels slower in crown glass than it does in air. So now it's your turn to try a couple of problems. So problem number 1, what is the speed of light in zircon? Calculate that and then show me the answer. And then problem number 2, calculate the angle of refraction when light travels from ethyl alcohol into zircon at an angle of 58 degrees. If you have any problems with either of these questions, just review the sample problems that I did for you earlier in the video. Once you have the answers, show me.